Modeling and analysis of structures with negative Poisson's ratio. Abstract auxetic structures are the structures with negative Poisson's ratio and display the peculiar behavior of lateral expansion when they are stretched, which is different from conventional structures. They get equal and opposing densification when compressed. Lightweight, high strength, impact damping capabilities, and stiffness offers potential applications in the field of aerospace, automobile crash box, implantable devices, military protection equipment, suspension mount, intelligent actuators. The present work is focused on analyzing the directional auxeticity of tetrachiral materials through design and analysis. The practical predictions about the global elastic properties of auxetic structures, such as reentrant hexagonal cell, reentrant star, reentrant triangular and lozenge square structures, are obtained with parametric 3D NX.11.0 and ANSYS 19.2. A fused deposition modeling in technique is used to build prototypes of auxetic structure. The analysis of the structures clearly established the auxetic behavior of all the considered models. Lateral expansion. Keywords: auxetic structures, negative Poisson's ratio, ANSYS, lateral expansion, strain, finite element analysis, NX 11.0. 1. Introduction. The terminology of auxetic was used by Professor Ken Evans of the University of Exeter. One of the first artificially produced auxetic materials, the RFS structure, diamond fold structure, was invented in 1978 by the Berlin researcher 1. Peach. Although did not use the term auxetics, he describes for the first time the underlying lever mechanism and its lateral expansion, therefore considered him as the inventor of the auxetic net. The earliest published example of a material with negative Poisson's constant is due to A. G. Polyakov in 1985. 2. Determination of the average characteristics of elastic frameworks. The next auxetic material came to prominence in science in 1987, entitled Foam Structures with a Negative Poisson's Ratio by R. S. Lakes from the University of East Coast in Madison. The use of the word auxetic to refer to this property probably began in 1991. 3. Designs of composites with inverted hexagonal periodicity cell, auxetic hexagon, possessing negative Poisson ratios, were published in 1985. Auxetic structures are efficient cellular materials that can absorb blast or impact energy through plastic deformation, thus protecting the structure. They are developing sacrificial solutions with lightweight, high specific strength, high specific toughness and excellent energy dissipating properties, due to its negative Poisson's ratio nature. The use of auxetic and non-auxetic panels in blast-resistant structures had been employed by developers. Nonetheless, implementation of those energy dissipators, explicitly as a uniaxial passive damper, is restrained to limited studies, which highlight the potential need for further explorations. For when a material is stretched, there is normally an accompanying reduction in width. A measure of this dimensional change can be identified by Poisson's ratio, V equals LAT strain/long. Strain, where long. Strain and LAT. Strain means strain in longitudinal direction and strain in lateral direction when material is compressed or stretched in axial direction. Auxetic structures are those with a negative Poisson's ratio and display the unexpected property of lateral expansion when stretched, as well as equal and opposing densification when compressed. They expand and shrink like this due to interconnected network. This unique property offers enhanced functionality in the property of structures. Compared to conventional structures, negative Poisson's ratio, NPR, structures offers increased plane strain, tunable density, fracture resistance, shear modulus, acoustic response. The NPR structures have been considered for a wide range of smart and functional devices, including smart antennas, stretchable sensors, protective equipment, and in many other applications from the fields of nanotechnology and biomedicine to defense and aerospace. Despite these advantages, they got difficulties in manufacturing due to complex design and limit their applications. For many reports, they are focused on theoretical and material response. Different types of NPR structures also have been developed. These are categorized into several types such as chiral, reentrant, rotating and honeycomb, and others. They found that 2D chiral and 3D geometries have highest negative Poisson's ratio and 3D pyramid has lowest. The design or modeling of auxetic structures can be done by mechanical softwares like NX, CAD, Creo, Kasha, SolidWorks. In this project, we selected NX 11.05, Siemens POM Solutions, as our design software. The analysis of these structures is done by ANSYS 19.2. 2. Design and analysis. The auxetic effect of 4 different geometric structures including reentrant hexagon, Evans, arrowhead, triangular, reentrant star, 4N, lozenge square were examined. 8. The geometries of each structure are shown in figures 1, 2, 3 and 4. Finite element analysis 11-12 with tensile loading conditions was performed on all these geometric structures using ANSYS package version 19.2. For each design, top surface was fixed to a rigid structure and the top surface was pulled with various input forces to calculate elongation in axial direction and transverse deformation. The characteristic strut ratio H/L and reentrant angle have significant effects on the properties of auxetic structures. The following all geometries are modeled using NX 11.0. 3. Results and discussions. The 4 structures reentrant Evans, arrowhead, reentrant star, lozenge square expands in the transverse direction as predicted and are shown in Fig 5, 6, 7 and 8. This confirms the auxetic behavior of the geometries. The elongations of Model 1 are as follows. Length x equals 6.72 E002 m. Length y equals 0.11281 m. Length z equals 1. E002 m. The Poisson's ratio of reentrant Evans is -1.88. The elongations of Model 2 are as follows. Length x equals 8.8115 E002 m. Length y equals 9.877 E002 m. Length z equals 1. E002 m. The Poisson's ratio of arrowhead is -1.12. The elongations of Model 3 are as follows. Length x equals 0.14242 m. Length y equals 9.433 E002 m. Length z equals 1. E002 m. The Poisson's ratio of reentrant star is -0.6623. The elongations of Model 4 are as follows. Length x equals 9.5741 E002 m. Length y equals 0.12306 m. Length z equals 1. E002 m. The Poisson's ratio of lozenge square is -1.367. Fabrication. The materials generally used for preparing the auxetic structures are polylactic acid, acrylic butadiene styrene nylon, titanium, nickel, steels and AM materials. Generally the auxetic structures are difficult to manufacture even though, the suitable technique for manufacturing auxetics is additive manufacturing techniques 9-10. In this work we fabricated the 3 models of our structures using PLA and ABS materials by 3D printing machine using FDM as shown in Fig 9 and 10. 4. Conclusions. Auxetic materials have unique mechanical properties and excellent shock absorbing capability. In this work modeling and analysis of auxetic structures were done using 3D NX.11.0 and ANSYS 19.2. Out of all the 4 structures considered, reentrant Evans structure has the highest negative Poisson's ratio which implies the better auxetic behavior. The auxetic property can be obtained in products manufactured by additive manufacturing techniques. We have successfully fabricated the models in fused deposition modeling using PLA and ABS.